Okay, so what we're going over today, guys, is just some introductory stuff on graphing. We will talk a little bit about how to construct a graph by hand, although we are probably not going to do very much of that. Okay, in this course, we'll be mostly doing our graphs using Google Sheets, okay, in this class, or if you like to use Microsoft Excel and you know how to use that, you're welcome to use that as well. You just have to copy and paste the graphs into your labs and whatever else when we're doing those. But we do most of our labs graphs electronically now, just because it's neater, it's easier, and it's way more accurate than drawing them by hand. Okay, so we will be doing that, but we will still go over kind of the nuts and bolts of how a graph works. Okay, what kind of things should be on it, right? All that kind of stuff. Cameron. No, it was not. There should be some stuff in there on graphing. Yep, I'm looking at it in a bunch of other people's notes right here. Right? Is it lesson 8? Well, it doesn't say lesson 8. It says right after lesson 6, right after the one we just did on scalars and vectors. Okay, so if we go to scalars and vectors, it should be the next thing. Okay, in there it should look just like this. All right, what's the purpose of using a graph? What's a graph for? Okay, to show data, okay, quickly, easily, visually, okay, as opposed to looking at a chart. Not always in a chart do you necessarily see the trend or the relationship between two variables, right? And that's what a graph is designed to do, is to show us the relationship between two variables, right? There are several different kinds of relationships that we'll be looking at in this course, okay, and you'll need to write these down because they're not in there, all right? We'll be looking at linear relationships. Okay, in a linear relationship, when your manipulated variable increases, your responding variable also increases. Okay, and usually does so by a similar factor. All right, so a linear graph would look like that. Okay, when your manipulated variable goes up, okay, your responding variable goes up. All right, remember that this is the x-axis here and this is the y-axis. Manipulated variable always goes here. Responding variable always goes on the y. Okay, other kinds of relationships, inverse. Okay, in an inverse relationship, it's kind of like a linear relationship except the other way. That means that as the manipulated variable increases, the responding variable decreases by a similar factor. Okay, meaning if I was to double the manipulated variable, the responding variable would probably be cut in half. Okay, that would be an inverse relationship. All right, other types of relationships that we will look at, exponential. Okay, and an exponential relationship looks like this. Okay, it's a curved line upwards. In an exponential relationship, what we usually have, okay, is that whatever increase in x happens, y happens squared, cubed, or to some other exponential power. Okay, so in other words, if I was to double my manipulated variable, my responding variable would go up by a factor of 4. Okay, if I was to triple it, it would go up by a factor of 9. Okay, squared. That would be a squared or exponential relationship. All right, and then the other kind is the opposite of that. Okay, inversely exponential. Looks like that. It's the other curve. Okay, so as the manipulated variable goes up, the responding variable goes down exponentially. You don't see this one all that often, at least not in this course. Yes, Cameron? Oh, yep. I got to go all the way back up anyway. Okay, now oftentimes in labs that we do in this course here, the problem we'll be investigating in the lab will be what's the relationship between this variable and that variable. All right, and so by making a graph and looking at its shape, we'd be able to tell pretty quickly. right? And then we'd be able to, do our analysis. The analysis would usually include making the graph, okay? And then in the conclusion saying, based on the graph and the data, there's a linear relationship because, the points went up in, a linear fashion, or they went up in an exponential fashion, whatever. Okay, so the graph is important for telling us the relationship between the two things we're investigating. Everyone follow me there? Okay. How many people are taking math right now? Are you into graphs already? Okay, good. So this is all going to be pretty much the same. All right. So if you're plotting a line graph and you're doing it by hand, it should always be done in pencil. But again, we're not going to be doing too many of these by hand because, well, why would you if you could do it another way? All right. So you draw your vertical axis, which is obviously the y-axis, and your horizontal axis, which is your x-axis. Okay. Time pretty much always goes on the x-axis. Anytime time is a variable or a factor in your experiment, it's most likely the manipulated variable, unless you can make time run faster or slower. I don't think you can do that, so we're probably not going to be doing too many experiments where time is the responding variable, all right? Because usually time just runs of its own accord and we can't do much about it. Okay. All right, so third thing, manipulated variable always goes on the horizontal axis. Definitely got to know that. Okay, responding variable always goes on the y-axis. Okay, when you're doing this in like a spreadsheet program like Google Sheets or Microsoft Excel, you always make the first column your manipulated variable. Okay, that way it shows up on the x-axis. They just kind of default to that for some reason. All right, and you should always include your units, okay, with your labels on each axis. I'll show you tomorrow when we have the Chromebooks, okay, how you label axis and all that kind of stuff on your on Google Sheets so that it shows up in your graph as a proper format. Okay, graph should also always have a title, and again, there's an easy way to do that, okay, in all of the programs as well. If your graph is ever missing any of these things, it does cost you marks because then it's hard to tell exactly what's on the graph. Okay, if I'm looking at a graph and there's no title, no units, okay, no labels, all I see is points, and that doesn't tell me very much. It tells me the points have a certain relationship, but I have no idea what they represent, and then the graph is kind of useless. Everyone follow me there? Okay. All right, the other thing we have to include, not just the labels, but the units are also important. Okay, if I'm looking at a graph and it says time and there's no units, I could be looking at something that's moving very, very fast or something that's moving incredibly slow. All right, so for example, if this was not, let's say, speed, let's say this was distance, okay, and it was measured in meters, and then time, and it didn't have any units, all right, I might think that this thing is moving, 20 meters per second, because I would assume the x-axis would be in seconds, but instead, since they didn't have any variables, it was actually supposed to be days. So have I made a grievous error in my assumption? Yeah, and not by any fault of my own. I thought I was looking at something that was moving pretty fast, okay, like let's say 10 meters per second, when in actual fact it was something moving at 10 meters per day. All right, yeah, kind of a big difference. All right, so units are crucial when you're writing and making a graph. Otherwise, your data is really hard to interpret. All right, choosing a scale. Now, this has kind of always been the tough part of making your own graph, okay? But choosing a scale is important because we want all of our numbers to fit on the graph. All right, and that seems to be the part that people have the most trouble with, even though it's very, very easy. All right, all you have to do to create a scale that works is count the number of squares that you have along each axis, and then divide your biggest number by the number of squares you have, and then it'll fit. Okay, everyone follow me there? All right, so to choose your scale, okay, all you have to do, okay, is take your biggest number, okay, so determine your scale by dividing the largest number on your scale by the number of squares. Okay, works every time. Now, sometimes you'll get a decimal. So what if I get like this, and I get 23.3 repeating? What should I make each line worth? 24. Have to make it bigger than 23. Because it says if I used every single line would be worth 23.333. If I make each line worth 23, is it going to fit? No, because that's less than the number they gave me. All right. So we we always round up. Okay, and we try and round up or use a number that's close to the number the calculator spit out, but that's easy to work with. Obviously, I'm not going to make each line on my graph worth 23.3 repeating. Okay, because that's not an easy number to work with. But 25 is. Okay, it's very easy to count by 25s, right? 25, 50, 75, 100, right? It's easy. Okay, so our next logical number up that would be a good one to use on our scale would be 25. All right, if I was, doing another scale and it spit out, like, let's say 3.7, I would round up to 4. 4 is an easy number to count by. I'd make every line worth 4. All right, why wouldn't I round up to 10 from 4? Too much of a gap. And then my numbers that I'm graphing run out halfway along the axis, and I only use half of my graph paper. Okay, so my graph ends up being kind of scrunched, and it's much harder to work with. It's much harder to get a best fit line and slope calculations and all that kind of stuff when your graph is this big. All right, so we always want to make it so that it takes up as much of the graph paper as possible. General rule, 80%. Okay, don't round more than 80%. Right. All right. Now, when you're filling up your scale, so if you're actually doing this by hand, okay, we said we would round this 23.333 to 25. So my first line would be 0, and then 25, and then 50, and then 75. But you can see as we get along here, those numbers get really scrunched together. All right, makes your graph kind of hard to read. I don't have to put a number on every single line. If I go 0, 50, 100, 150, will people understand that every line is still worth 25? Yeah, because I've left some lines blank, but it's a lot easier to read. Okay, again, we're not going to do many by hand, but it's important you understand how this kind of works. Okay. All right. We're going to cross off number 8 because we don't do that. It's just in there, but we don't do it. Okay, and the name for the point 0, 0 is called the origin. Cameron. Will you have to write what on the... We'll see. Most of the time I make the graph and I have you interpret it, just because it's a better use of time. Yeah. All right, questions so far? Everyone's good with this so far? Okay, like I said, most of the time we're going to be doing these on Google Sheets or on Excel because it's just way easier to do. Okay, and we don't have to worry about neatness and all that kind of stuff. All right, this kind of stuff is important whether you're doing this on the computer or by hand. Okay, finding the slope of a line is probably one of the most important things you do with a graph, because the slope of your line tells you unequivocally the numerical relationship between the two things that you were investigating. All right. So if, for example, I was investigating, let's say, what we're going to do tomorrow, which is carts moving along the floor of the atrium, okay, I would have position in meters and time in seconds on my graph. All right. I'm going to be recording how far they go every 5 seconds. All right. That's what we're going to do tomorrow. And so I'll have some points along my graph that look kind of like this. Something like that. All right. What do I want to find out about these carts? If I know, I can already find out how far they've gone and how long it takes them to do that. But what do we usually use distance and time to calculate? Well, distance and time would calculate speed. Yeah, see, that's a trick. It's a scalar quantity. Okay? All right, so they would probably calculate speed. How do I normally calculate speed? What do I do with distance and time? I divide them. Okay? That's the formula, right? V equals d over t. So if I was to be looking at this graph, and let's say I'd drawn a best fit line, something like that, that was much straighter because I would use a ruler. Okay? The slope of that line would tell me the average velocity of my cart through the entire trip. Sorry, average speed of my car. See, I made the same mistake. Average speed of my cart over the whole trip. Okay? Because all the way along that line, if I pick any point on that line, okay, and divide its y value by its x value, I'll get the same number. Okay? Everyone follow me there? All right, so that line represents the speed of my cart. So what I want to be able to do is find its slope. Okay? To find slope, you use this magical little formula here. Okay? Oh, sorry, it's not on here. We'll talk about it in just a second. Okay, little terminology here. Okay, grid lines. Grid lines are the lines on your graph. Okay, that make up the grid. That's pretty straightforward. Gridline intersection. Okay, are spots where the grid lines cross each other, like this one and that one. Everyone good with that? Again, this is not something you're going to use much because Google Sheets will actually do this for you. All right. X-axis, obviously horizontal. Y-axis, okay, is your vertical. Best fit line, okay, takes an average of the plotted points. Drawing a best fit line is actually kind of tricky, right? And you do need to know how to do it. Yes, Google Sheets and Excel will draw one for you, but you still need to know how to do it. Because I might ask you, given a graph that's all constructed with everything except a best fit line, I might ask you to draw one. Right? A best fit line always follows the trend of your points. Your best fit line always follows the trend of your points. Sign language should write this down. Okay? If I slow down and say something twice, it's important. Okay? It always follows the trend of your points. It doesn't have to start at 0, 0. Okay? A lot of people seem to think all best fit lines have to start at the origin. They don't. They need to start wherever they can best follow the trend of the points. Okay? This one started at 0, 0 because my first point was 0, 0, and that was the place I could draw it that best followed the trend of my points. But if I have a graph and it looks like this, would I start a best fit line at 0, 0 for those points? No, because that would not allow me to follow the trend of my points. Okay? It would look like this. Well, that doesn't follow the trend of my points at all. All right? So I don't want that. All right. What would follow the trend of my points would be a line that looks more like this. All right? Didn't start at 0, 0, but it follows the trend of my points. Everybody with me there? Okay. As I often have people, they get a graph that looks like this, and they don't know what to do. They're like, okay. Really? That's what I say to that. Really? Okay. Your best fit line has to follow the trend of your points, so it should look like that. That way its slope is negative, just like what your points are doing. Okay? Because this is saying that as your manipulated variable gets bigger, your responding variable is getting smaller. That's a negative slope. Okay? I need my line to show that. All right? Everybody follow me there? Okay? So the big thing to remember is your best fit line always follows the trend of your points. Make it start wherever it needs to in order to do that. Okay. All right. Now, when you're calculating the slope of your line, okay, so you draw your best fit line, and usually when you do that, it'll go through some grid intersections, okay, on your graph. Everybody follow me here so far? Okay, goes through some grid intersections. What you need to do is find 2. All right, you need to find 2 grid intersections that your line goes through. Or if your line does happen to go through the origin, you can use the origin as a grid intersection. Okay, you can also, if it goes directly through one of your plotted points, you can use that. All right, most of the time, your best fit line will not directly center through one of your plotted points. All right, so generally, you're looking for 2 points that are on your line. Okay, and I enunciate that because this is what I often see. A person makes a graph and their points go something like this. Okay, and they draw a best fit line like this, and it doesn't go through any of their points. And they calculate the slope of the line by using this point and this point. Okay? That's calculating the slope of this line. Is that the same as my best fit line? It is not. That is why you cannot use points that are not on your best fit line to calculate the slope of your best fit line. Does that make sense? Yes? Okay, we got to make sure we do that, because that is the most common mistake that I see. Okay, people draw a beautiful, perfect, best fit line and then use 2 points that aren't on it to calculate its slope and ruin everything. All right, I don't want you to ruin everything. You got to use spots that are on your line, and that's why we want to try and use grid intersections. Okay, the reason we want to use grid intersections is we can go directly across to each axis and find out the exact values of those points without having to estimate anything. Okay, does that make sense to everybody? All right. Now, to calculate the slope, we use this handy dandy little formula. How many people have seen that before? Slope is rise over run. Okay. How many people have seen this one before? Only one. Okay. It's actually the same thing, and I'll show you why in just a minute. All right. So slope is rise over run. It's also written like this: y2 minus y1 over x2 minus x1. Okay? So rise is the change in y, or the change in height. Okay? X is the change in the horizontal value. Okay, so at this, the bottom here is the change in x. All right, so the change in whatever our x-axis is. Everyone all right with that? All right, so if I was using this graph right here, okay, this point would have both y2 and y1. This would be y2 and x2. Okay, this point here would have y1 and x1. How do I decide which one's 1 and which one's 2? Yeah, whichever one happens first on the x-axis. Okay, whichever one happens first on the x-axis. And the reason I say that is because if you have a graph that looks like this, okay, this has to be y1. Wow, that was terrible. y1, okay, and x1, okay, and this has to be x2 and y2. Okay, it always has to go by the x-axis. We're okay with that. Okay, so when calculating the slope, all we do is take y2 minus y1 and divide that by x2 minus x1. And that gives us the slope of the line. How much it goes up while it's going over. Okay, so for a graph like this one, where it's distance traveled in kilometers divided by time in hours, it's going to give us the speed. All right, we can always tell what a graph will give us by looking at the units that we're dividing. Okay, on the top I'm going to have kilometers minus kilometers, which is kilometers, over hours minus hours, which is hours. So kilometers divided by hours is kilometers per hour. I'm calculating speed. Okay, if I was, looking at, let's say, kilograms and weeks, okay, my slope would be in kilograms per week. Okay, could be like a graph of someone's weight loss, okay, something like that. All right, now the other equation that we sometimes use in graphing is y equals mx plus b. Okay, this y is a y value. All right, you would get that from a point. Okay, so it's the y value of a point you've chosen on your graph. Similarly, that's what x is. It's the x value of the same point. Okay? Anyone remember what b is? It's the Y-intercept. Okay? Okay? The Y-intercept is where your best fit line crosses the y-axis. So this spot right here would be b. Everybody right with that? Yes? Okay. M is the slope. Now, at this point, a lot of people go, can't I just use rise over run code error? It just seems so much easier. It is, but you don't always have necessarily enough information. Y equals mx plus b is really handy, okay, for extrapolating. That is, finding things that go beyond your graph. Okay, that may not appear on your graph, but happen after. Now, let's say I wanted to calculate slope. I want to get m by itself. What should I move first, x or b? B. Remember, that half rule that we had, move what's not attached to what you're looking for first. Okay, so I'm adding b right now. If I want to move b, what do? Subtract it. All right, so I'm going to have y minus b equals m times x. All right, how do I get x over to the other side? I divide. No, I want to get x over. Divide by x, right? Okay. All right, so this is slope. I've gone y value minus y value over x. Is that similar to this? In fact, it's exactly the same. Here's why. Here's where b is. What's the value for x right here? 0. Is this the same thing? It is. Okay, so I've got, let's say I was using this point here, I would have this value minus this one divided by this minus 0, which is still the same thing. I'm still calculating the slope of the line, and it still works. All right? You can use whichever way you choose to do that. Okay. All right, now this part here about height of the triangle divided by the width of the triangle. I want you to circle that, and then I want to explain something about the dangers of height and width of the triangle. I often have people make this mistake, and they just do this. The height of the triangle is 1, 2, 3, 4. And the width of the triangle is 1, 2, 3. Is that going to give me the right slope? It is not. Because each line was not worth 1, each line was worth 500. Kind of a big difference. Okay? That's why I don't like this height of the triangle by the width thing. Just get rid of it. All right? It's no good. Okay? People make that mistake because they read that in their notes and assume it's the right way to do it. Okay? What we mean by height of the triangle is change in y divided by the width of the triangle, change in x. Okay? Not actually counting the squares. All right? Questions so far? Okay. Here's what we're going to do. I'm going to pass out some graph paper, and we're going to build this first graph together. All right? And then I'm going to have you try some others. Okay, so here's what we're doing. We're doing an experiment, which is not very exciting, investigating what happens when I increase the diameter. What happens to the circumference of the circle? What should happen? It should get bigger. Okay? Will that be a linear, exponential, inverse, or inversely exponential relationship, do you suppose? Probably going to be linear. Okay? And what is usually the relationship, numerical relationship, between diameter and circumference? Pi, right. So what should the slope of my best fit line on this graph equal? Pi, yes, it should equal 3.14. I don't know what past that because I'm just not that nerdy. Okay, I don't know pi to 1,000 places. Okay, yeah. All right. Now, we're building this graph. If we're building a graph by hand, I'm manipulating diameter. Where should it go? On the x-axis. All right, so I'm going to make my x-axis diameter. No, don't sing it or it'll get stuck in my head. Okay. All right, our diameter's in centimeters. I already have a Weird Al Yankovic song stuck in my head because of that. I know pi to 1,000 places. How many people have seen the video for White and Nerdy? That's like my theme song. Okay. Yeah. All right, circumference. Okay, also in centimeters, which is important because pi has no units, and when I divide centimeters by centimeters, they'll cancel and I will be left with no units. All right, so I've got my axes labeled with units. Okay, I need a title on my graph. Okay, diameter versus circumference, not very creative, but it'll do. Okay, now I've got to decide on my scale. I've got 30 squares on my x-axis, and the biggest number I need to fit on my x-axis is 7.4. So I've got to figure out what to make each one of those lines worth. So, okay, I'm going to take this number here and divide it by 30. I'm going to get a decimal here, right? Is that okay? Sure it is. Okay, it just means that each line's not worth very much. Okay, Bill, question? No. No, I don't. Okay, so 7.4 over 30 is going to tell me what each line on this graph should be worth. On 7.4 divided by 30. All right, so each line should be worth 0.246. How about I round that to 0.25? That an easy number to count by? Yes, it is. Okay, so we're going to make each line worth 0.25. That also means that I don't need to put a number on every line, because that'll get really messy, especially with my handwriting. Okay, so I'm going to make every fourth line 1, because that's what works. Okay. And look at that. My biggest number is going to fit on my graph. That's great. My biggest number is 7.4, and it goes all the way to 7.5. Okay, I got to do the same thing with my y-axis now. I have 37 lines on my y-axis. Okay, so I'm going to go 23.1 over 30. All right, each line should be 0.77. I can probably round that to 0.8, right? Okay, it's easy enough to count by 0.8. If I go up to 1, I'm really not going to use up my whole graph. Remember we said the rule would be about 80%? Well, 77 over 1 is 77%. That kind of doesn't make the rule, right? Oh, sorry. Yes, by 37. Yes, you're right. That's going to give me probably a better number to work with. Good catch. 3.1 divided by 37. All right, 0.62. Okay, let's go with 0.7. How's that sound? Okay, we can all count by sevens? Yeah. All right, so each line's going to be worth 0.7. All right, so 0.14, 28, 0.42. I botched something there. Oh, yeah. That's it. I've got decimals. It's supposed to be 1.4 and 2.8. Okay, yeah. Gee, I really got to finish that coffee. Okay. 1.4, 2.8, 4.2. I was like, I'm never going to get to 23.1 at this rate. I'm not even to 1 yet. Okay, 7.0, 8.4, 9.8. That's much better. Okay, and then 14 more. Okay, I'll stop there because I only needed to fit 23.1 on. Okay. So I made each line worth 0.7, but I just went every second line, so it didn't get as messy as it would have got if I had made made a number on every line. Because I'm not going to pretend that that's neat either. All right. Once I have both axes on there, can I start plotting my points? Sure. Okay. So that's what I'm going to do. I'll use a different color here so we can see them a little more clearly. All right, so my first point is 1.8 and 5.6. I could also assume, even though it's not on here, that a circle with a diameter of 0 would have a circumference of also 0. I know that's not on here, but I'm going to make that assumption because I know it's true. All right, so 1.8. All right, so this is 1.75, so 1.8 is just slightly past that. Okay, and 5.6. All right, so there's my first point. 2.8 and 8.9. All right. Should be right about there. Okay. 3.2 and 10.2. Oh, whoops. That's why that didn't look right. It's 2.8's back here. Yeah, that's better. Okay. 4.4 and 13.8. Okay, so that would be 4.5. So 4.4 would be here. 13.8 be about there. .6 and 20.6. About there. Okay, and 7.4 and 23.1. All right, I've got my lines plotted. Sorry, my points plotted, not my line. Now I need to draw my best fit line. Okay, this has to be done with a straight edge of some kind. All right, you cannot freehand a best fit line because you'll never get it straight. All right, since I can't use a ruler on the smartboard because it gets really confused when you set a ruler on it. Okay, I'm going to cheat, and I'm going to use the line drawing tool. Okay, which always draws a very straight line. And I'm going to start down here. All right, there's my best fit line. Okay, if you've got a ruler or another sheet of paper, you can just use the edge of another sheet of paper to draw your best fit line. Okay, draw it so that it follows the trend of your points. Now, did all of my points get on the line? No. Okay, because there's some error in where I put them. I can't be certain I put them exactly on those points. I did my best. All right, so now I want to find two grid intersections so that I can use rise over run to calculate the slope. All right, so I've got lots of grid intersections. I'm going to use that one. And let's say this one. They're nice and far apart, although it doesn't matter if they're right next to each other. They're on the same line. Okay, so now I want to calculate the slope. So we got to remember that slope, oh, still have the line tool on. And can't erase those. All right, so slope equals y2 minus y1 over x2 minus x1. So for my graph, y2 is 19.6. Right, now you see why picking a grid intersection is a good idea. Really easy to get your point values. 19.6, okay, and minus 1.4. All right, same thing for the x values. All right, 6.25 minus 0.5. All right, so we'll see how well I drew this. I have several times actually got 3.14, okay, when doing this graph, so I'm kind of under pressure now to do this well. 19.6 minus 1.4 divided by 6.25 minus 0.5. Oh, it's pretty close. It's pretty close. Okay? If I was having you draw your own best fit line, what I usually do on a question like that, if it's on an exam, is I draw 3 best fit lines. One I think is just a little too steep, one I think is just a little bit too shallow, and one I think is wonderful. Okay? And I accept anything between I think is slightly too steep and slightly too shallow. Okay, so there's a bit of a range of accepted slopes that I would allow. Okay? If yours is way outside of those, your best fit line was kind of way off. Okay? All right, so we got 3.17. It's not great, but it's close. Everybody with me there? Okay, what are the units for that? Doesn't have any. Remember, these were in centimeters, and so were these. Centimeters divided by centimeters cancels. All right, that's why we have no units on pi. Okay. Making sense? All right, flip that graphing paper over. You should still be able to see the lines through. Okay, on the other side, be a little bit tricky, but okay, I think you'll be able to manage. And I want you guys to graph this graph. Okay? Now, here's what we're going to have. Okay? The force on the elastic band is going to be our manipulated variable. Okay? This is going to be our responding variable. Can you not see the lines through? Have extra? Oh, thanks. All right, I want you guys to graph those two things on your graph. I'm going to give you a few minutes before I draw mine up here, okay, and then we'll compare and see how close we are. Okay, if you're not done your best fit line and calculating your slope yet, don't worry about it. I'm just going to do mine on here, okay? So I've got the scales on there, okay, units, all that kind of stuff. I've got my points plotted, okay? Now I'm just going to put my line on there. Okay, something like that. I think follows the trend of my points pretty well. And then I'll find my grid intersections. Okay. One right there looks pretty good. And one right there looks pretty good. Okay, so I'm going to do this one two ways. I'm going to use y equals mx plus b, and I'm going to use rise over run. See if we get kind of the same answer. All right, so to use rise over run, okay, I'm going to have my y2 minus y1 over x2 minus x1. Okay, and so that's going to be y2 is going to be 16 minus y1, which is going to be 10.4 over 4.8 minus All right, so how about that? We're getting exactly 2, okay, here for our number. 2. This was in newtons, and this was in centimeters. So what are my units? Newtons per centimeter. Okay, basically how much force you would have to apply to stretch, okay, the elastic band. Well, to stretch the elastic band 1 centimeter, you would have to apply 2 newtons of force, okay, is what that slope is telling us. Now, if I want to calculate using y equals mx plus b, all right, I'm going to use this point right here as my point, and then here's b down here, okay, my y-intercept. So I want to get m, which is the slope by itself, and we've already said that that means y minus b divided by x. All right, so my y value here, okay, is the same as it was here, 16, okay, minus, and this is looking like we've got 6.4 there, right, over this x value, which we said was 4.8. 16 minus 6.4, okay, divided by 4.8. It's going to give me the same number, 2. All right, so either way will work. It's y equals mx plus b is nice when you have a very clear y-intercept, okay, like you do on that graph there. All right, because what's this y-intercept telling me? If you're stretching a rubber band, does it have length before you even start to stretch it? Yeah, that's what it's telling me. Okay, the rubber band has a length of 6.5 centimeters when it's not stretched. Okay, when there's no force being applied to it. All right, so little things like that, being able to interpret graphs is really important. That's an important skill that we want to develop in this unit. Okay. All right, how many people have got a slope there? Okay, I would say that probably on this graph I would accept anything between, let's say, 1.8 and 2.2. Okay, it's kind of a range, right? Because there's not really a lot of kind of slantiness on that one. All right. Okay, last one here. Relating the number of sheets in a book to its thickness. So, manipulated, responding. Number of sheets, thickness of the book. Okay, try this one on the back. Okay, I know it's hard to see the lines through, but rather than burn another sheet of graph paper, okay, see if you can do that one on the back. Okay, give you a few minutes. We may not get to that one before class is over, but you can get it started. Okay, and tomorrow we'll start out the class by showing you how to do this on Google Sheets. Okay, then we'll go and do our graphing lab in the atrium, okay, collect our data for the little carts and get started on that, and we'll have that on Wednesday to kind of continue working on that stuff.